And philosophy is to know, the ability to deductively predict with certainty. We will expose concisely what occurs in science since we believe that a description dissipates a lot of misunderstandings. Mathematics. Mathematics is the activity of the mathematicians consisting in, once chosen the formal approach, a choice, by the mathematician, of logic, such as the classical logic, the minimal logic, the intuitionist logic, the multivalued logic, the modal logic, the paraconsistent logics, the constructive logics, the temporal logic, each one developed by the logician, logic which is deductive and not inductive, are their mathematics based on inductive logics, where he chooses what is the syntax, what is a proof, what are the rules of inferences in order to go from one assertion to the other in a proof. The second choice pertains to one of a recursive set of axioms so that it is possible to verify manually whether any formula belongs to the set, which is devoid, as much as possible, of direct ontology since what matters now is axiomatic, in axiomatic mathematics, of the relations between the formal symbols. This becomes a key point in the language. We no longer ask directly what is a plane, but how it interacts with the other concepts in geometry, such as a point or a curve. In natural languages, some stronger degree of direct ontology remains, in asking, in contextually, what is a chair, even though we can take the stance that, in a formal language, the relations of a concept towards the other concepts can be deemed ontology, and ontology throughout the relation. Naturally, there are mathematicians who are against the deductive axiomatization of mathematics, in the sense of an axiom as a definition which must thus be accepted by other mathematicians, as opposed to a common sense, an intuitive truth. They believe that there must be some initial axioms, in the ancient sense, where those axioms are intuitively valid for every person on earth, past, present, and future, irrespective of their ambient culture. Let us think of the paradox from Malaise. The axioms as a definition are not convincing nor persuasive, especially if those are not intuitive. Typically when their advocates seek a minimal number of axioms a la reverse mathematics, minimality is often seen then as a beauty. The mathematician a la cons rejecting the formalization, the logicization of the mathematics calls for a primitive mathematical reality, typically via the arithmetic or geometry, which would be whatever existed before its exploration by the mathematician, before the categorization, through induction, of these primitive mathematical entities. The mathematician perceives the disorganized mathematical reality, such as most people seem to perceive the disorganized phenomenological reality. Even when the mathematician bundles his personal intuitions into a system where some deductive rules connect the intuitive statements, the task of seeking an axiomatization remains. Can we claim that what is mathematics is such systems of intuitions connected by some chosen rules of inferences before they are axiomatized in formal logic? Naturally, the axiomatization of the field of study enjoyed by a mathematician is difficult. The axioms attempt to capture and organize some patterns that the mathematician enjoys. The task consists in finding a set of independent axioms and seeking a result on the consistency as well as the completeness of the theory, here theory as a mere set of axioms. From the work by the logicians, we recall briefly that the soundness of a deductive system of some logic means that what is derivable formally from the syntax will be true semantically, whereas the converse, the completeness of a deductive system of some logic means that each true theorem has a proof, consequently true syntactically, deductively. The equivalence between soundness and completeness exists for the classical logic of propositions and predicates. From the work of Gödel on the incompletenesses of some formal system attempting to encode the arithmetic, the crucial questions become: what does the logician do, once that he is not assured that his favorite logic is complete? Once that he is assured that his favorite logic is incomplete, what does the mathematician do, once that he is not assured that his favorite theory is consistent? Once that he is assured that his favorite theory is inconsistent. Other mathematicians can accept the axiomatization but still reject other classical constructions. Belonging to those are the predicative mathematicians a la Poincare and Weyl. Even though the predictive mathematics splits into classical and constructive, the two predicative branches agree on the rebuttal of every, or rather almost, impredicative definition, self-referencing definition such as the axiom of the power set, that every set possesses a power set, which is thus a new set. In being constructive, the constructive predictive mathematician rejects equally the excluded third, the principle of omniscience a la Bishop. The mathematicians rejecting the infinite sets, such as n, are called the finitists. Those radicals rejecting the finite sets of large cardinals are the ultrafinitists. In passing, we note that even in doing classical mathematics, many natural toposes, with the object of the natural numbers, appear to be general toposes, in the sense that they lack the excluded middle or the axiom of choice, thereby restraining, that is to say in generalizing, the mathematics to the intuitionist case. Fortunately, many theorems in classical mathematics remain valid in constructive mathematics. The topology is the most famous field which gains in going fully predictive, thanks to the locale theory carried in positive constructive logic. The task of the mathematicians is thus to derive as many theorems as possible, without knowing in advance how many there are, within the chosen definition of the theorem, of the valid intellectual step in the proof, belonging to the choice of the logic. Thus far, the traditional mathematics has been done in deductive logic, most of the works in deductive classical logic. Hopefully, soon, we will have the computers to carry all our proofs. All that will remain for humanity will be to seek new logic and new axioms. However, we can bet that this last task will be done by our machines sooner or later. The mathematical logic and the theory of the proof rely on what can be known, in one word, a judgment. There exist three famous dichotomies of knowledge currently deemed relevant by humanity: deductive inductive, analytic synthetic, necessary contingent. Each philosopher, logician, a mathematician will like one dichotomy and connect it and, perhaps, refine it or redefine it completely to, at least, another one of the above, or a new one, and will likely praise or, on the contrary, will abhor the other connections, refinements, redefinitions that the other intellectuals made. Let us expose too concisely the analytic synthetic judgments a la Kant, since it connects to a part of the mathematics of today. The philosopher Kant was the famous thinker of this dichotomy on knowledge, attempting to reach one synthesis. After his friend the empiricist philosopher Hume widened the chasm between the rationalists and the empiricists, threatening to annihilate the entirety of the philosophy, whereby every pursuit of knowledge, the philosophy, is traditionally displayed as the activity about truth, which would be bad apparently. Kant chooses to modulate the analytic synthetic with the dichotomy a priori a posteriori, or equivalently, necessity contingency. He swiftly concludes that an analytical judgment which is also posterior of observation is a contradictory judgment. The analytical judgment, a priori, is what is obvious, purely logical, evident by its analysis, by the analysis of the judgment itself, obvious by its definition, its meaning, what requires not a proof, not exhibiting one evidence, solely the reason is required to conduct us to the veracity of such judgments. Naturally, since the definitions themselves do not come ex nihilo, but rather from experience, the definitions will be very debatable about their frontiers, or even about their mere relevance. One definition will be intuitive for one, not intuitive for the other. One person will have such affinity towards a definition, another person will not. The other kind of judgment is the synthetic judgment a posteriori, where to accept a statement as truth, we must first understand its meaning as for the analytical judgment, but equally must see, from the world, at least one valid evidence, one valid proof, one valid construction. Typically, for the existential quantifier in predicative constructive logic, once a criterion of validity is chosen, evidently, we fall back on intuition, for each step of this proof must either be analytical, elementary or possess proof, evidence, a construction. In the theory of the constructive types, the analytical judgment that is of type alpha translates into a synthetic judgment. The type alpha is true, itself translating, by definition of the truth in intuitionist logic, into the type alpha exists in establishing the existence of at least one element belonging to the type alpha. In terms of the proposition, as type alpha, we must provide at least one proof denoted A. The synthetic judgment a priori remains the task of Kant. Now the proper problem of pure reason is contained in this question: how are synthetic judgments possible a priori? Such a judgment pertains solely to the sheer intuition which concerns mathematics, metaphysics, the morality. This is the point of bifurcation of Kant from the empirical realism from the United Kingdom, that there is a reality and we cognize it, more or less approximately, only after our senses feel the reality, to the transcendental idealism, in trying to incorporate the rationalism at the time on the continent. Kant manages to suggest that time and space were synthetic a priori. They are concepts universal as well as necessary and stem from us. In mathematics, some claim that the synthetic judgment a priori concerns the field of Euclidean geometry, rather than the arithmetic, such as would advocate Gödel, who considers that the mathematical intuition, especially the set theory and its traditional axioms, are forcing themselves upon one as true, and ideally, after the gradual addition of some axioms, would permit to solve every mathematical problem to grant the wish of the mathematician Hilbert. In the theory of the constructive types, the calculus of the analytical judgments is decidable as well complete in the sense of Gödel, since what is required to be decidable is to be derivable. Syntactically, let us say, from the formal rules, and what is required to be complete is that none concept besides those which are in the analytical judgment through its constants is required for the judgment to be derivable, whereas the calculus for the synthetic judgments is incomplete and undecidable. For the establishment of the belonging of at least one element of type alpha is not assured. Indeed, via the correspondence from Curry, Howard, the intuitionist business of finding at least one proof to establish firmly the existence relates to the finding of an algorithm, a program on a computer with the further constraint that the algorithm must halt. The halt of any quest of the exhibit of at least one element belonging to the type that we attempt to establish as true may never happen. Finally, since there can be more than one proof to each theorem, it is natural to ask when two proofs are equal. This question leads to the one of the identity. The field of study chosen by the mathematician depends on his affinities as well as the open problems of his time. In his attempt to put the mathematician inside the mathematics, the open problem is what a famous logician Cavales denotes as the call of the mathematics by the mathematics themselves. The becoming of the mathematics comes from a necessity within them. This discussion addresses the autonomy of the mathematics, of their meaning, their direction, less about their experience, by the mathematician, without motivating many of their questions. In the path of a philosopher called Desanti, this view no longer holds. Formal mathematics cannot answer all the mathematical questions, such as one of the adoptions of the axiom of choice. As aforementioned, there exist some programs on the computer displaying, for a few proofs, each elementary step, each syntactic transformation from one statement to another. The will to clarify the jump from one proposition to another one leads to a more natural calculus of propositions and predicates, a la Jensen, than the contrived calculus a la Hilbert and its overused material conditional, or even material implication, logical implication. The binary connector between well-formed formulas, that is the material implication, belongs only to a few logics and its interpretation depends on each of those logics. In classical logic of propositions, the material implication is indeed present and is found on one of the two levels, the syntactic level, where the connector is taken for granted, or even, via the law from De Morgan, a mere shortening of lambda, for instance, or the semantic level, where this time, the arrow is no longer a logical connector, but a function of truth, that is to say, that the arrow takes 2 degrees of truth in 0, 1, and outputs 1 degree of truth in 0, 1, according to the famous truth table defining. A priori, from the perspective of degrees of truth, the binary logical implication is not tied to the causation, the deduction, even though the material implication connects indeed to the causation in the form of the deduction theorem as a meta-theorem of first-order logic with the typical rules of deduction. Finally, the perspective of the material implication as a function of truth leads to the famous paradoxes of material implication. The logical deduction, the entailment of a statement from a set of statements, becomes the application of, at least, one of the chosen rules of inferences to the premises, in order to obtain the conclusion. The prime illustration of the rules of inferences is the modus ponens as well as the modus tollens. When the set of premises is empty, the conclusion is called a theorem or an axiom. Each rule of inference is a relation on the set of all the formulas syntactically correct in our desired language. The rules of inferences remain at the syntactic level, even though, most of the time, each rule of inference must preserve the notion of veracity, at least in classical logic. When each premise is true, semantically, we are bound to see the conclusion equally as true, semantically. In intuitionist logic, the chosen rules of inferences must preserve the notion of probability or justification. The rules of inference turn the proofs of the premises into a proof of the theorem, or in other terms, the rules of inferences turn the justified assumptions into a justified theorem. An argument is in consequence valid when the argument, the application of various rules of inferences, preserves the justification of the assumptions throughout all the sentences used up to the final theorem. The notion of intuition, of naturality, of evidence of a deduction seems to always refer to a notion of necessity, that which cannot be otherwise. The tragedy is obvious that no universal intuition amongst humanity exists, thus far. What is intuitive for one, is contrived for the other. What makes sense for one, remains ridicule for the other. What is beautiful for once, is ugly for the other, etc. Once these intuitions bundle together, only a field of claimed necessities is left to us in the quest, for the realists-rationalists, to find the few claimed necessities which is more necessary, more appealing universally, than the other claimed necessities, whereas in seeing the world positively, as being, that is to say as being enough, we are left only with a plurality of contingencies, of sufficiencies. Nowadays, most people attribute this diversity of claimed necessities by lack of agreement, by a bad erudition from a bad education, the word bad meaning, of course, which is not their erudition, which is not their education. In passing, we recall that Kant did consider that the most interesting mathematical statements ought to be synthetic a priori, universal and necessary. We are left with a typical question such as, how can we say that the geometries which are not Euclidean can be intuitive truth, especially when we never have perceived them, whereas one type of this geometry seemed natural to simultaneously and independently two mathematicians, Lobachevsky and Bolyai. After that, the mathematician Greenberg asks Gödel if he believed in some intuition of these spaces, such as our intuition of the Euclidean geometry. Gödel went further, all alone, in insisting on the validity of the transcendental ideality à la Kant of the flow of time, of the flux of instants bringing a personal decomposition into past, present, future, even in those non-Euclidean geometries which would nuance becomingly the notion of simultaneity once passed down to the physicists, in suggesting that an objective lapse of time, temporal flow typically measuring the change leading to a notion of objective change is not possible in his metrics as solutions of the equations of the general relativity from the physicist Einstein. The proper time of the privileged, mobile observer, that is the cosmic time built from the mean density of matter as in the traditional universe, is homogeneous and isotropic, cannot be accomplished globally in his metrics. The mobile observer is the one who remains at rest relatively to the mean distribution of matter, regardless of the expansion of the universe. When there is such an expansion, it is, therefore, the sole observer who can talk about change typically as the displacement of the matter in his frame of reference. Nonetheless, all Platonist as he is, Gödel claims that since that, at least, one such solution of those equations obeys the same laws as our universe, that his universe lacks the property of existence of the mobile observer, that the existence of the flow of time precisely means that the flow of time exists in every solution, he leads us to claim that, even in our universe, we lack the property of existence of the mobile observer globally, on a large scale. Let us note that he takes the stance of a cosmological semantic, once interpreted the energy tensor as the matter density of a homogeneous distribution of swirling dust particles. Briefly, the particles of dust are interpreted as galaxies, once we wish to see the solution as describing a space-time, full of matter, with a non-nil cosmological constant. Finally, let us note that the existence of the closed time-like curves in the static version of his metric renders problematic the notion of temporal order. Naturally, since many do not find intuitive all the aforementioned consequences, these metrics displease as a model of the concept of space-time, that is to say, that they are rejected instantly, by most, as a model of the concept of space-time. When we have left with a perspective on knowledge or even truth through human deduction, we bounce once more on the finitist view of the demonstration. What is a valid proof that is not read by anybody but its authors? What is the place of the proof of the famous classification of finite simple groups which took thousands of pages? What is the place of the proof when most mathematicians are doubtful about its validity, perhaps even its authors, when most mathematicians become more and more confident of the validity, but some authoritative figures in the field remain not convinced, not persuaded, skeptical? Can we trust proof exhibited by a computer? Can we trust the creator of the program to give us proof? If we do not understand the proof outputted by a computer, can we be certain that this lack of comprehension stems from us, instead of being a true fault in the program? Most mathematicians denigrate the logical aspect and choose classical logic. In order to mock them, we can say that they love the law of excluded middle since it is too difficult for them to carry the mathematics constructively, for they were not trained to love weaker logics, this bad education aforementioned. Once more mathematicians are acquainted with other frameworks, they might teach them to the students, even though the passage from the research to the teaching takes as long as the acceptance by the community of the new field that only a few persons on the planet study beforehand. Naturally, the choice is not one framework, logical or theoretical, or the other, but rather that the students go from weaker frameworks to stronger frameworks to see what theorems fail one after the others when they play with the axioms. This provides a finer understanding of the field with new horizons. The plan is not to say that the traditional mathematics must be abandoned, but that they are very good to trim some fields, to quickly determine some results, to swiftly grasp what happens. The second step is to see how far can these results hold in frameworks, weaker, more general, more robust. In the same manner, a history of mathematics cannot hurt and would emphasize the problems that mathematicians attempt to solve. It will take a few generations of mathematicians to develop and trim the field, to pass it to the classical mathematicians, to teach it to graduates, to teach it to undergraduates, to communicate it to the physicists, for the physicists to use it such as the mathematics of today, for the physics students to learn it. 2. Physics. Physics is the activity of the physicists consisting in providing some models of the phenomenological world, models often called objective, once assumed the metaphysical stance of realism rationalism, of naturalism, of scientism whose choice depends on each physicist. For instance, we can think of the various models to determine the temperature in the various layers of the atmosphere, where each continent possesses a model, more or less broad in geographic terms. We have seen that mathematics could well be written in natural languages, such as it was a few centuries ago, before the birth of mathematical, formal, logic. The same holds for physics. All the laws in physics can be statute in natural language. The law held for many centuries, the shortest distance between 2 points is a straight line, needs not to be encoded mathematically, nor logically. Nowadays, we would say that this law became the shortest distance between 2 points is a geodesic. Once we refine the original statement through the experiences and conceptualization. In physics, besides the existence of some reality more or less, accessible by humanity, via the senses or the reason, we assume that the descriptive mechanism, as well as the deductive predictions, are what matters, in order to speak of the posited reality. In fact, the predictions through deductive logic are more crucial than the decomposition by the causation of the initial phenomenon of interest by the physicist. Indeed, the predictions are now what discriminate between the models, the mechanisms. To refute a mechanism is not a direct refutation of it, but a refutation through the predictions obtained from the model and the application of the deductive logic chosen by the physicist. A good physicist sees the world, and better, he sees it through a description, likely via causes and consequences, through the predictions that it retrieves from the mechanisms. These two aspects of the task can be done qualitatively, quantitatively, in a language natural or formal. In physics, nobody knows, thus far, whether the equations derived, thus far, by humanity concerning their experiences do hold in other parts of the universe. This is mild solipsism, humanist solipsism, analog to the old question on how to know whether China exists, if we never have been to China, especially given that we have seen other humans lying beforehand. Every knowledge seems to have a degree of solipsism. What does it mean to know something beyond a direct perception? In all cases, any other kind of solipsism would be ridiculed, if not frowned upon socially, in our times. This mild solipsism remains crucial for our modern justice, where the judges judge the subjects on acts, speeches, and far less easily on intentions. People are good enough to be subjected, but without concrete, real evidence, we are not sure of their motives, of the whys nor the hows of their acts, speeches, thoughts. The truth in the tribunal stems essentially from the evidence as well as the deductive application from this evidence in order, for each party, to reach some statements, in the hope that those would be persuading enough the other parties. Naturally, each party has its own deductive rules, has its own affinities, its own perspectives, and the use of the natural language obfuscate greatly the principles adopted by each party. Nonetheless, whatever the experience, in order to acquire some information about it, we create our tools to convert the phenomena into a datum, likely quantized, perceived through the senses that we believe that we will have when we discover the datum. If the capacity at the reason is what matters, there is no reason, thus far, to say that physics discovers the nature of reality. There is no logic in order to say that to predict some phenomenon is to know the world, to discover the reality. We can only remain on the logical tautology that to predict is nothing but to predict, that to provide a mechanism is to provide a mechanism. Even if we have a mechanism which leads to the most accurate predictions that humanity has ever seen, there is nothing telling us that there is not another model with different mechanisms which leads to the same predictions on a domain identical to the one of the first theory. In other words, still under all the assumptions in the field of physics, containing especially the plurality of mathematical proofs of mathematical theorems, there is nothing suggesting that there is the uniqueness of our models. The plurality of the perspectives on the phenomenon brings thus the question of the identity of two physical theories, besides the plurality of two proofs, two mechanisms, in mathematics. Moreover, a crucial situation is the interpretation of the mathematical theorems, obtained by the physicist via a mathematical deduction from the current mathematized model, modeling the currently studied phenomena, since the custom in physics is to analyze the physical behavior of some system through the new theorems, obtained by the aforementioned deduction. That is to say, the new theorems no longer model the present phenomena, but they're now a new ontology of the reality, through the deductive logic, we obtain new equations which we believe describe adequately some phenomena, perhaps a refined understanding of the original phenomena, but generally, the physicist seeks new ones. The validity mathematical deduction which was thus far disconnected from reality is ascribed the power to describe what has never been perceived. The logical validity becomes the reality. This is rationalism. The proofs themselves of the new theorems derived by the physicist are viewed by humanity as the physical mechanisms itself, as usual via the causes and consequences, but oddly enough, not the proofs and theorems of the mathematics used beforehand, by the mathematicians, leading to the mathematics used by the physicist. If all the mathematics used beforehand, by the mathematicians, were considered physically relevant, the physics would instantly become metaphysics since the mathematical foundations whereon the physics lies would be ascribed some ontology, plausibly the same ontology ascribed to the new concepts and equations derived by the physicist. What does it mean to exist? For the mathematical and logical results preceding all the mathematical results considered relevant by the physicist. For instance, what does it mean for the rule of inference used by the physicist that is the modus ponens to be real, to describe some reality which remains more or less inaccessible, therefore unknown? Besides this voluntary ontological cut, each step of the derivation of these equations is now tied to the reality. The question arising is the potential plurality of the mathematical proofs of the same theorems from the identical initial mathematics and ultimately logics. In passing, we note that a few persons suggest that every phenomenon relates somehow to mathematics, that every phenomenon is ultimately a mathematical entity. In detail, it is not any mathematics, but a form of constructive ones. The immediate question is if there is one mathematics relevant for everything, why are there other conceivable mathematics? If there is mathematics that describes every phenomenon, then can these constructive mathematics explain why other mathematics, typically, the classical mathematics, are possible and even more, lead to some predictions, more or less accurate, once humanity applies them to their endeavor of explanation? The remaining task of the physicist is to extract as many statistical predictions as possible. Can this be performed by a computer? Where lies the ingenuity of the theoretical physicist? Since physicist relies on mathematics, logic, and philosophy, we know that they take all the assumptions of these disciplines in their stance about their work, in the communication between the scientists, between the scientist and the public. More explicitly, in science, there is a choice, by the physicist, of many things, of postulates, axioms, principles, methods of deduction, method of induction, methods for collection and treatment of experimental data. The famous physical principles assumed by most, if not all, of the physicists today are the principle of causation, of causality, stating that the consequence appears always after the cause, the principle of locality, the principle of least action, which is more mathematical than anything else, and others which are peculiar to a field or even to some models in each field. To this day, physical activity has been the forcing of these principles on our perceptions. It is the unmotivated will to plate the phenomenological world with the few principles that we have, at the time of the perception. Typically, we choose to plate the reality with the causation or causality and retrieve as much information as possible through this choice. Many people cherish dearly this method, in stepping towards the stance that this choice is relevant and whatever the data that we obtain, those are genuine, authentic, and more appropriate than any other methods, once established some purpose to justify the methods. In a religious context, the pious do not wait for a transcendental being to manifest itself in order to pray it, contrary to what a scientist would urge us to do, imploring the reason, the logic. The same applies in a scientific context, where the scientist does not wait to have an umpteenth mechanism to motivate the principle of cause and effects. Nonetheless, he dares to claim that the reality obeys this principle, in order to apply the causality, the perspective of the whys and the hows, via the daily faith that the scientist has in it, even though the reason itself leads not to such a faith. The output of the scientific method is a variety of models, more or less overlapping, which describe as well as predict statistically, more or less broadly, more or less probabilistically, more or less quantitatively, more or less qualitatively, more or less accurately, some phenomenon assumed, by the humanity, to be repeatable within a framework determined by each model. What is absolute bits of knowledge? There are two, in essence, logical mathematical. The first is the outputs of one model. The second is the comparison of the outputs of the models when the outputs overlap according to the physicist. The second knowledge will provide a method to grade the models, relative to one another. A model will be ranked higher than a second if the theoretical predictions will be better, especially once these theoretical predictions are compared to the experimental data, up to the falsification of the model when the predictions are not at all recorded. This situation leads to the notion of simulation. Classically, a simulation is to know exactly, from an initial condition, the final condition after an evolution, typically temporal, of the system. If the predictions are verified, the evolution is called deterministic. By the solipsist degree of knowledge, we do not know if the model works before crunching the numbers and compare with the phenomenon. In passing, let us recall that the quantum mechanics outputs deterministically the final state after a temporal evolution of an initial state and equally outputs deterministically the probabilities of the final state as well as of the results of a measurement, instead of outputting deterministically the final state as well as the results, such as it would be the case of measurement in classical mechanics. It remains thus that the notion of a simulation of measurement in quantum mechanics cannot be about the bijectivity from the initial state to the final state, but rather about the bijectivity of the initial state with the ordered pair consisting of one probability associated to its final state. Nonetheless, the interpretations of these probabilities are plural, a plurality leading to difficulties. We recall equally that there are several interpretations of the quantum mechanics which can be, badly, categorized as either realist or epistemic. Most of the physicists currently subscribe to the interpretation called Copenhagen, which asserts that the wave function is epistemic. The realist quantum mechanics suggests that the wave function is not epistemic but ontological, that the mathematical device that is the wave function is an element of reality. Another realist quantum physics sees the probabilities as degrees of truth, but disregards the wave function as an ontological object, since it tries to reformulate the quantum mechanics without this notion, as it is customary in quantum logic. For the epistemic, to this day, only two interpretations of probabilities are offered in pure mathematics. The first is the frequentism, where the probability is the ratio of the number of observed events over the number of all the events theoretically possible. In one word, a frequency or propensity of the results once the experiment sufficiently repeated, for the frequentism to be applicable, relevant. In pure mathematics, the second doctrine called Bayesian can be axiomatized by various systems, but there exists equally a subjective justification of this doctrine where the probability becomes a degree of belief, quantized confidence of the observer in the tested model. It is said that the two probabilistic perspectives coincide when their domains of application overlap, and these two have made their way in the quantum mechanics a la Copenhagen. Each choice, by a person, of a model, is a matter of affinity, of belief, of preferences, of traits of character, of will to be crude in the quantization. More concretely, we can measure, with a ruler R1, what we believe to be a thing, we obtain the number x1, we choose another ruler R2, we get the number x2. The number x2 will always beget, at least we believe from some induction, in the application of the ruler R2 to the thing to be measured, if the second ruler R2 is used. Perhaps, from the applications of the two rulers, the two numerical results are equal. If we assume some objectivism, typically, from the realist rationalist stance such as the example implies thus far in this particular phrasing, we might even think that these two equal numbers are indeed real, that they make sense since they are both equal to the true numerical length, true length which is, thus far, a human concept but which is assumed to exist at every time, once we chip the time in a succession of temporal moments, especially before every measurement. There is a true world, a true property of the world, or at least of the things in the world. Every measurement will approximate the reality, the objectivity through the numbers that the measurement delivers to us. These assertions typical of a realist have been somehow undermined by the Cauchy-Specker theorem in quantum mechanics, a famous negative result a la Bell, where the notion of the contextuality of the potential observable seems to become crucial. The theorem suggests that it is contradictory to assign simultaneously some values to every possible observable, especially when the observables do not commute between one another, whilst holding the functional relations between these observables. Functional relations which seem natural to expect from the observables to the point of these being the classical relations of the classical mechanics. Once the methods, the algorithms that are the two rulers, have been built, the typical question is what orders can be put between them. Naturally, being absolute, this question does not lead to an answer. An answer is possible if we have a purpose, a problem beforehand. Why is there a problem beforehand though? There is no necessity to use the R2, nor even the R1. There is not even the necessity to see the rulers as measuring devices. There is not even a necessity to measure anything. Why do we want to measure something? What is the problem having for answer the measurement? Each model describes, more or less partially under realism rationalism, a phenomenon. If we venture on the whys and the hows, we engage ourselves in what is beyond the physics, beyond the phenomenon and its acquirement by the senses, or in one word, we engage ourselves in metaphysics. This stance can lead quickly to some non-monism since those questions become separated from the physical experience, even more so if those questions suppose realism beforehand. Here, objectivity is the numbers, the quantization of each phenomenon. The objectivity relates to the repetition of the process, as well as to the prediction. We believe that the quantitative data aforementioned are more objective than qualitative data, precisely because we believe that numbers are more objective than qualities, for they are derived from some deductive algorithm, from some process more or less repeatable and more or less intuitive, whereon every human agrees, throughout time and space. We retrieve here the universal egoism from the period called the Enlightenment. Naturally, this is dubious and we see that it does not hold once the scientist goes in the society telling his results to other persons. Once cast the choice of the person about this algorithm, yet remains the task to convince or rather to persuade the other persons that her choice is right, better, relevant. In the following step, each person chooses the models that she likes the most and endlessly debates politically with the other persons in asking which method is better than the other, which must be applied in such fields, in such social doctrines. So much for the universal agreement on some model supposedly intuitive. We see that the physicists are always at the frontier of the explainable in terms of mechanist models. The physicist is interested in the domain where its favorite models do not work, whereas the domain where the physical models do work is left to the engineer throughout the industrial technology in order to solve some concrete problems. This is why the scientific is considered sometimes as an artist, to use the bad dichotomy scientist-artist, since he creates what has not been created. The engineer does the same, for he creates something that was not existent, nonetheless with more constraints, since he retrieves the theories from the physicists. We See, in all this, that the tragedy of the scientific method is its inability, thus far, to advocate or prove, scientifically, since it is all about proofs, its necessity, and its sufficiency towards the goals set up by humanity for this activity, that is to say, towards the acquisition of knowledge about the phenomenological world. To this day, we can only say that the product of the scientific method is a few descriptions, without being able to pretend to a uniqueness of the description, as well as to predict and to compare the experimental data to the theoretical ones. Can we go beyond? If so, whose task is it? Under a monist stance, especially physicalist or naturalist, where everything is independent of the humanity, the physical realism begins here, and everything is nature, the humanity and its thoughts included, the sciences must explain, the rationalism begins here, then what the humanity categorizes today as metaphysics. Why do the human deductive models which predict, accurately or not, do predict? Why are the maths so useful in physics? Einstein asks, useful towards what standards of usefulness? If we answer those, we can thus say why the physical models are necessary and sufficient to predict the quantitative and qualitative results. Nonetheless, depending on the answer, we still may not know why it is a good idea to predict, or we may understand that it is actually a bad idea, with respect to some purposes, either retrieved from the answer or chosen by humanity, once the population has the answer. In gastronomy, after many inductive generalizations in the cuisines, each chef develops a strong intuition of the flavors, the fragrances, the textures of each, state of the freshness of each ingredient known to him under the various preparations. The task of a chef is thus to create at least one original recipe which will please the most people, pleased by its taste and perhaps through its health benefits. Based on their intuitions and their beliefs in the inductive knowledge, the best chefs foretell what mixes of ingredients will produce a satisfying dish. As typical of the molecular gastronomy, the most realist of the chefs will dare thus to claim that, from their accurate predictions of the flavors, fragrances, textures of the final dish, they would have discovered an objective knowledge about the reality of the ingredients as well as of the perception of taste. Thus far, the theoretical physics is gastronomy. We have plenty of recipes, from a diversity of chefs, with each recipe, cooked by each chef, giving us, over time and over the chefs, some dishes more or less identical, yet we lack a motivation to claim that some recipes bring us the best knowledge about the reality, beyond what works once predicted, since we still do not know what the reality is, especially in physics, beyond what each team of experimental physicists perceives and claim to be in agreement with the models. What conducts us to think in terms of reality in physics, but not in gastronomy? 3. Philosophy. These questions lead to philosophy. Since antiquity, philosophy is the activity of the philosophers, those who love the Sophia. Clearly, the philosophers are not sage themselves, but only that they love the Sophia. At the time, from the Greek perspective, philosophy is the activity to live the good life, once we have found the truths. Nowadays, the philosophia is divided from the sciences to such an extent that there is the famous cliché of a vague continental philosophy where the philosophers are the most disconnected from the sciences, and an analytic philosophy where the philosophers are supposedly more rational, even though they do not hesitate to go as far as asking dubious questions such as if we are transported on Mars, what moral doctrine should we adopt upon encounter of the Martians? The philosophical departments are, physically, disconnected from the scientific ones, just as the mathematical ones are separated from the departments of computer science. All these dichotomies are more detrimental than anything else. Let us illustrate. Far away from the spaces devoid of points which themselves speak, in branching out, of the constructing for a discussion, anew, of the motivation of the usage of the typical Archimedean space that is invoked from the analysis for the values taken by the functions coding the observations, to the topology for the relativistic spaces, to the statistics for the values of the probabilities which were first dominantly Bayesian, then dominantly frequentist, thought nowadays as either Bayesian or frequentist, then after all, of its construction which leads us, in particular, to the questions of points and spaces of points as foundations, that is to say, the number and aside, its ontology by its computability. Far away from the spaces devoid of points which themselves speak, in branching out, of the constructive logic, thereby of the mathematical proof, whereas a bunch of theorems in mechanics remain as expressible as provable in this logic, thereby inviting us on questioning the necessity and the sufficiency of the kind of tools in mathematics, consequently in metaphysics, for those seeing the mathematics as far more than a mere technical method. The philosophers put back the ontology in the language, natural, contrary to the mathematicians who attempt to relegate the ontology, the meaning on the logical side, even though an ontology more or less faint remains when the proofs are carried on the semantic side, instead of the syntactic one even on the syntactic side, some ontology remains in the choice of logic. The philosophers do not hesitate to talk about what is not real. Let us take the concept of the idea. An idea is not real, but it is a pure being. An idea is a pure ontology, it is a thing that is not another thing, the purity defines, at least in part, the idea. The traditional example is the one of justice. What is the idea of justice, what is justice? Why does Plato talk about the concept of an idea? Plato talks about this concept, put it higher than anything else, for it was important in its time, it solved a difficulty. Plato was looking for the selection of the pretenders, to the magistracy, let us say, since there is competition in the democracy, as established by the Greeks. How to select the persons, with respect to some purpose. The concept of the idea solves the problem of what gives somebody the right, or not, to something. In the terms of the philosopher Deleuze, the task of those philosophers is to create some concepts, through the creation of problematics. The philosopher creates and does not discover. He must identify, at his time and location in space, in his culture, what are the problems in his society. This step is incredibly more difficult than it appears. What matters less is the solution to their identified problems, especially if the solutions stem naturally from the good concepts created from a good outline of the problems. The identical situation applies in science according to the philosopher Bachelard. The problems are not self-defined. If nobody asks a question, there is no problem and knowledge. The two perspectives from Deleuze and Bachelard are eminently theological, contrary to the common view remaining utilitarian, therefore consequential. We no longer create a solution in order to gain, to retrieve some utility, but to answer a clever problem. Nonetheless, a plurality of solutions could remain. If we replace mathematics with the doctrine of a philosopher, the description works equally. Indeed, each person seems to have her world, her language, her logic, her intuitions, her obvious facts, according to her, and inferences of facts, inferences which are logically obvious, once more according to her. In one word, each person has her own truths, her own history, her own context, a la paraconsistent logic that is the discursive logic. Two worlds, two contexts are confronted when two persons talk. They need a dictionary to understand themselves since too many times, generally, long after the beginning of the discussion, they understand that they do not even agree about the definitions of the keywords that they use, for the natural languages have too much vagueness, circularity, and emphases. In passing, let us note that this laxness of the natural language did not stop Spinoza to write his work in a mathematized form, a succession of deductions of statements from some definitions, axioms as well as theorems previously derived. If by some miracle, two persons have an efficient dictionary between their languages, that they agree on the definitions of the terms of one another, then it remains not assured that they share the same ideas, the same ideology, the same course of actions, and speeches. Evidently, along many of the natural languages developed around a realist stance, with any wish to surpass some degree of the trichotomy object-medium-subject becoming difficult to express in those languages, a state and a national education will fix most of the experiences of the people belonging to the nation. But, for each individual, each definition of each word will have a fixed core, of elementary shared intuition, with an added nuance or subtlety that each individual adds from his proper experience. For each philosopher, we choose to follow the deductions that he makes according to the logic that he chooses. Since philosophy is done in natural language, there is more vagueness, emphasis, circularity than in mathematics, because the words of the natural language have more ontology since it is the task of the philosophers to do this. At some point in the deductions of the philosophers, we will be surprised, we will disagree, we will not follow the deduction because, in a logic foreign to us, each logical elementary step is intuition or imagination which depends on our affinities as well as our capabilities. This is where we continue, stop to believe in his doctrine or learn another one, or explore our own philosophy. What we retain from all these ideas, ancient and modern, all these models of the world, all these stories concerning the whys and the hows, all these trendy intellectual fields changing generations after generations, all these discussions on necessity, purposes, sufficiencies, particles, causes, evil, atoms, effects, ontology, knowledge, right, truth, proof, reality, fields, freedom, ends, intuition, reason, mean, wrong, bad, objectivity, will, morality, God, causality, induction, waves, locality are much noise.